Okay. Yeah. So thanks for the opportunity to present my work at this conference. My name is Navaneeth Ravichandran. I am an assistant professor in the mechanical engineering department at IISc Bangalore. So today I'll talk about the work that I have done to develop a unified first principles computational framework to predict the phonon thermal and thermodynamic properties of semiconductor materials. So this work has been funded by these agencies, Boston College, the US Department of Energy, and Office of Nuclear Research, and a couple of graduate fellowships at Caltech and West Institute. So my research focus, just to give you a broad overview, is to develop new computational and experimental tools to probe the microscopic interactions among energy carriers in electrically insulating and semiconducting materials. So using these tools, I have worked on problems such as discovering new material candidates with extreme thermal properties. For example, here I'm showing a couple of pictures of new materials that we discovered using this framework. One of them is this boron arsenide single crystal. Another one is an isotopically engineered enriched form of boron nitride crystals, both of which have a thermal conductivity exceeding 1000 watt per meter Kelvin at room temperature. And I've also worked on experimentally probing interactions of heat carriers, in this case phonons, at nanoscale interfaces and boundaries. So you can find more information about these works in these papers. So in this talk, I will only focus on the computational materials discovery project to predict new material candidates with extreme thermal transport properties. So in these semiconducting materials, phonons, which are the eigenmodes of a perfectly periodic harmonic crystal lattice, are the main heat carriers. In fact, they control both thermal transport and thermodynamics. So these phonons have, as you may all know, have a characteristic phonon dispersion, which is a relation connecting the frequencies to the wave vector. You can define quantities such as the group velocity, the energy at which, the rate at which the energy is transported, which is given by just the slope of these curves. So these phonons in a real material also undergo interactions among themselves because no real material is perfectly harmonic, and they always have some inherent perturbative anharmonicities which drive these phonon-phonon scattering processes. So these phonon-phonon scattering processes can occur among 3 phonons at a time or 4 phonons at a time and so on. And a net total of all of these scattering processes can be summed up, that is the rate can be summed up to give a single quantity gamma, which is the total scattering rate. So knowing these properties like phonon frequencies, group velocities, and scattering rates, you can put them together into a kinetic theory expression to calculate the thermal conductivity of any material. So the expression here shows the thermal conductivity of a material is represented as a sum over all phonon modes in the crystal, that is the sum over the wave vector and sum over the polarization J of heat capacity times velocity squared divided by the scattering rates. So as I mentioned earlier, phonons also control thermodynamics because they contribute to the vibrational component of the free energy. So if you know the free energy of a crystal, you can essentially calculate various thermodynamic quantities such as equilibrium lattice constant, thermal expansion, pressure, bulk modulus, etc. at finite temperature. So recent advances over the past 2 decades in first principles computational technique have enabled us to very accurately calculate these microscopic phonon properties and therefore the microscopic thermal and thermodynamic quantities. So this first principles approach is predictive and it's free of any adjustable parameters. So to give you a quick overview of this first principles approach, all that we need to know to get the properties of a material is the crystal geometry, the types of atoms and the number of atoms that go into the crystal structure, and also a representation of the core and valence electrons in the crystal structure. That's it. So with just this information, we can crank it through the density functional theory machinery and calculate properties such as phonon frequencies, dispersion, the free energy, including the vibrational component, phonon scattering rates, and putting these all together, we can also calculate the total thermal conductivity of any material without any adjustable parameters. So in the red box on your left is one of the first examples of the work from my postdoctoral advisors group, where they use this density functional theory machinery to accurately predict the thermal conductivity of silicon and germanium over a broad temperature range without any adjustable parameters. So conventionally, this first principles approaches, people who have done these calculations typically restrict the calculation of free energy, that is the vibrational component of the free energy, to the harmonic term, and that's why this name quasi-harmonic. And also the thermal conductivity calculations are typically restricted to the case of interactions among 3 phonons only. So for the purpose of this talk, I will label this approach of using quasi-harmonic phonons and 3 phonon scattering processes as the conventional approach. So this conventional approach actually has been predictive beyond just silicon and germanium. For example, this is just a small list of the materials where the thermal conductivity has been predicted very accurately, thermal conductivity and thermodynamics, using this conventional approach. But naturally, at this point, a question arises. Is the conventional approach sufficient to describe the thermal and thermodynamic properties of all materials? So over the past 2 years, I have been developing a unified first principles framework, which includes higher order terms in the free energy and higher order interactions among phonons to answer this question, this precise question. Is conventional theory sufficient for all materials? In fact, using this for unified first principles approach extended beyond the conventional theory, I have worked on several interesting problems, such as predicting the ultra-high thermal conductivity of this new material boron arsenide, and as a consequence, a very unique non-monotonic pressure dependence of its thermal conductivity, and also found that the effect of higher order phonon scattering, for example, here 4 phonon scattering, that is scattering among 4 phonons, is actually quite strong and ubiquitous among a broad range of even common 3-5 semiconductors. So my work has led to identification of the ultra-high thermal conductivity form of boron nitride, that is C11 boron nitride, through isotopic purification. And finally, also extending the conventional theory to include higher order effects in phonon thermodynamics. For example, the case of strong phonon, anharmonic phonon renormalization in ionic crystal sodium chloride. So this is a broad overview of the work that I have done using this approach, but I'll only focus on this first topic in this talk. So the reason to go beyond the conventional theory and really develop this unified first principle framework was driven by a need to find high thermal conductivity material candidates. So as we all already know, diamond is the highest thermal conductivity material known to man. In fact, its thermal conductivity is more than 4 times higher than even metallic systems like copper and silver. So Glenn Slack in 1973 actually looked at all of these high thermal conductivity materials, that is thermal materials which have thermal conductivity more than say 300 to 400. And he found out several common features among these materials which give them the high thermal conductivity. So for example, if you look at the list on your left, all of these materials have very light constituent atoms. So we all know that when you have light atoms, you have high vibrational frequencies and high group velocities. And he also noticed that these materials have very simple crystal structure and very strong bonds, which means their anharmonicity, which drives phonon-phonon scattering, is also very weak. But as a surprise, in 2013, when Lindsay and co-workers did the calculations for several materials, they found out that their prediction using this conventional approach, that is with 3 phonon theory, they found out that the thermal conductivity of boron arsenide can actually exceed that of diamond beyond room temperature. So notice that boron arsenide has almost 3 times higher average mass than that of diamond. So it is a heavier material than diamond, therefore defying conventional guidelines that I presented earlier in the previous slide. Yet their calculations using 3 phonon theory, that is the conventional theory, predicted that the thermal conductivity is, could be higher than that of diamond. So before I go into my work on boron arsenide, let us first think about why boron arsenide's thermal conductivity is higher than diamond, even though the conventional guidelines predict the opposite trend. So to do that, let's go back and look at the thermal conductivity expression. And if you look at the phonon dispersion comparisons between diamond and boron arsenide, so because diamond is lighter, they have stiffer phonon frequencies, in which case the group velocity, which is the slope of these curves, is higher for diamond compared to boron arsenide. So clearly in the numerator for thermal conductivity, diamond wins over boron arsenide to get a higher weightage. But if you look at the denominator, that is the scattering rates, in this case the 3 phonon scattering rates, what they found was that the 3 phonon scattering rates for boron arsenide was unusually weak, almost 10 times weaker than that of diamond in this small frequency range. So this means that the denominator is smaller for boron arsenide than for diamond. So by having a smaller denominator, boron arsenide compensates for the smaller numerator, and eventually the thermal conductivity of boron arsenide even exceeds that of diamond at room temperature. So this shows that boron arsenide is achieving this high thermal conductivity in an unconventional manner, that is defying the conventional guidelines. So what causes this unusual weak 3 phonon scattering rates in boron arsenide? Let's go back and think about it from the dispersion perspective. So here I am showing the dispersion, phonon dispersions for boron arsenide. You have 3 acoustic and 3 optic branches. And because the boron arsenide has a large mass ratio between boron and arsenic, you have a large gap in frequency separating the acoustic and the optic phonons. Now let's think about a typical 3 phonon scattering process where you have 2 acoustic phonons scattering into an optic phonon. So any scattering process has to satisfy 2 constraints. The first one being the conservation of momentum or the wave vector. I have chosen these 3 points such that this equation is trivially satisfied. You can see that Q1 plus Q2 roughly adds up to Q3, which is the x-axis. The second constraint is the conservation of energy. So what it says is that the outgoing phonon's energy should be equal to the sum of the incoming phonon energy. And in this case, because of the large gap between the acoustic and optic phonon, this process is completely forbidden. That is, you cannot find any 2 acoustic phonons that can scatter into an optic phonon. So this 3 phonon acoustic optic scattering channel, which is actually one of the most dominant scattering channels in most other semiconductors, is completely forbidden in boron arsenide. So you remove one scattering channel completely from the picture, the total scattering rates go down, the denominator goes down, the thermal conductivity goes up. And that is the microscopic origin of why boron arsenide has such a high thermal conductivity, even comparable to that of diamond. So naturally, a question will arise at this point: what about higher order scattering involving more than 3 phonons? So clearly, you can see from this picture that if you add 1 more phonon to the mix, you can satisfy both momentum and energy conservation simultaneously. So at least from the constraints perspective, 4 phonons acoustic optic channel is allowed. But typically, scattering events involving large number of phonons is typically a higher order process in perturbation theory, and the strength of these higher order processes are expected to be weak. In fact, if you go back to the picture I showed you earlier, for the case of diamond, with just 3 phonon scattering calculations, they were able to achieve excellent quantitative agreement with the experimental data. So what this indicates is, in the case of diamond, 3 phonon scattering picture sufficiently describes thermal transport, and any addition of higher order scattering process should not change this curve significantly. But the problem is with boron arsenide, it is not available in nature at that time, so they could not conclude whether the 4 phonon scattering processes are weak enough in boron arsenide or not. So the fundamental question that I wanted to address is to estimate or actually quantitatively calculate the effect of 4 phonon scattering on thermal conductivity of boron arsenide. So before I show you some results, let me just give you a flavor of how challenging this computational work is to calculate 4 phonon scattering. So the problem boils down to actually just calculating the scattering rates. So if you have the scattering rates including 4 phonon processes, you can eventually get the thermal conductivity with very little work. So this process can typically be broken down into 2 sections. The first one is to count the number of scattering channels that are allowed according to the energy and quasi-momentum conservation constraints. And once we have this list of allowed scattering channels, we can calculate the strength of each and every channel. This is where the anharmonicity of the crystal comes in, which describes the strength of each and every channel. And putting these two together, we can calculate the scattering rates through Fermi's golden rule. So if you look at a typical conventional approach calculation, that is calculation involving 3 phonons for a reasonable grid, I think these numbers are for a 21 cube grid in the Brillouin zone. You typically have about 100 million scattering events of 3 phonon processes, and to calculate and store the strength of these events, you typically require 150 gigabytes of storage. These kinds of numbers are very doable these days. You can get this work done on a single compute node in a matter of a couple of hours. But if you look at the corresponding numbers for 4 phonon scattering, the number of allowed events go up by 4 orders of magnitude, and the corresponding storage also increases significantly. So when I first implemented this code, the first version actually took me several weeks to get a converged thermal conductivity number. But over the past couple of years, I have implemented several symmetries of the matrix elements involved in the scattering rates, scattering strength calculations, and also incorporated several hardware acceleration features to bring down the computational cost and the computational time to an order of 1 day. So having spent so much effort trying to improve the speed of the calculation, let's see if it's worth it or not. So here, just to refresh your memory, I'm showing the thermal conductivity of boron arsenide calculated using the 3 phonon conventional picture. So you can notice that at 300 Kelvin, the thermal conductivity exceeds 2000 watt per meter Kelvin. That is almost as high as diamond. If I include 4 phonon scattering, what happens is there's a dramatic decrease in the thermal conductivity from the 3 phonon value. In fact, at room temperature, you see that the thermal conductivity goes down by a factor of 2, and at higher temperature, it can go down by a factor of 5. So clearly, there is a significant drop and an effect of 4 phonon scattering on the thermal transport in boron arsenide. So before I proceed, if you remember, I had mentioned that for diamond, we expect 4 phonon scattering effect to be weak because we were able to get excellent agreement with the experiment with just the conventional 3 phonon approach. And that's basically what we get. When we did the calculation for diamond, including 4 phonon scattering, we hardly noticed any change in the calculated thermal conductivity. More importantly, we still got excellent agreement with the experiment over the broad temperature range. Okay, so now we have an algorithm or a first principles code with which we can calculate the properties of phonons very accurately. So with this code, we can actually go beyond just calculating thermal conductivity, right? So we can actually look at the microscopic origin of such a large reduction in thermal conductivity of boron arsenide. So to do this, let's go back to look at how the scattering rates compare between 3 phonon and 4 phonon processes. So once again, to refresh your memory, I'm showing the 3 phonon scattering rates of boron arsenide that I had calculated and shown earlier. So you can see that these phonons have very low 3 phonon scattering rates, and because scattering rates occur in the denominator, these phonons contribute the largest to the overall thermal conductivity with the 3 phonon picture. Now, if I add the 4 phonon scattering rates to this plot, you can see that 4 phonon scattering rates are the largest precisely in the frequency range where the 3 phonon scattering rates are weakest. So when you add these together through some kind of a Mathiassen's rule approach, you find that there is almost a 10-fold increase in the scattering rates at this lowest scattering rate point. So for example, if you see in this region, the blue triangles have been lifted up by a factor of, I think 4 or 5 or 6 to these purple points. So there's a dramatic increase in the total scattering rates by addition of 4 phonon scattering. So the denominator is going up in this thermal conductivity expression, so the thermal conductivity is dropping down. And this is the microscopic origin for why 4 phonon scattering is having a dramatic effect on thermal conductivity. Okay, so these are just computations, right? So how do we know these things are actually happening in reality? So to confirm that, we collaborated with our experimental colleagues who fabricated, actually grew these crystals of boron arsenide for the first time in a very pristine manner with very few defects, and they were actually able to confirm our theoretical prediction. So the black curve that you see here is a calculation, black solid line is the calculation from our work, including both 3 and 4 phonon scattering for boron arsenide. And this curve lies very close to their best samples, which are shown by the red circles. In fact, around the same time, there were 2 other competing groups who were also trying to grow boron arsenide crystals, and their experiments are also confirming our theoretical prediction that the thermal conductivity of boron arsenide is strongly affected by 4 phonon scattering. If you look at this middle figure here, the blue curve is the 3 phonon prediction, and their experimental curve match or roughly match the red curve both in rough magnitude and also in the trend.
8 minutes.
Sorry?
Just a sec.
Hello?
Yes.
Yeah, you have 5 minutes more of talk time.
Yeah. Okay, so one important point that I want to highlight is
मेरे पास तो support system नहीं आ रहा है यहाँ पे, about us आ रहा है.
Sorry, can someone mute her? Because
are you able to hear me?
About at
talk because someone is
about at because I'm not able to.
Yeah. Thanks. Yeah, please go ahead.
Yeah. So I just wanted to mention here that even though 4 phonon scattering is having such a large effect on the thermal conductivity of boron arsenide, the measured value in all 3 works is still exceeding 1000 watt per meter Kelvin. So to give you some perspective, silicon's thermal conductivity is only about 150 watt per meter Kelvin at room temperature. So this is about a 6-fold increase in the thermal conductivity. There's also independent work which shows that boron arsenide has similar electronic properties to that of silicon. So now you have a material which is as good an electronic material as silicon, but 6 times a better heat conductor than silicon. So you can really envision passively cooled electronic materials with these kinds of, with boron arsenide. So there are other materials also. So boron arsenide is not the only case where 4 phonon scattering is important. In fact, we have calculated the thermal conductivity, including 4 phonon scattering, for a broad range of materials spanning the entire 3-5 family. And we find that a number of materials, 4 phonon scattering, that is beyond the conventional theory, is very important. As you can see in these pictures, the solid lines are my calculations in this new framework, unified framework, and the dashed lines are the conventional picture. And the experiments are really lying on top of the curve without any adjustable parameters. So it's a very predictive scheme, which includes the reality of having higher order effects in thermal transport. But there are also materials where the effect of 4 phonon scattering is weak. So we do find some of the 3,5 compounds like boron phosphide, gallium arsenide, and silicon carbide, where the dashed and the solid lines are roughly overlapping or very close together, indicating that 3 phonon scattering, the conventional picture, is sufficient to describe thermal transport in these materials. So to give you a consolidated picture, here I'm plotting a histogram of the effect of 4 phonon scattering, that is K3 plus 4 divided by K3. And you can see at room temperature, all the 3,5 compounds with the green bars have a very weak 4 phonon scattering. And there are a few candidates, including boron arsenide, which have extreme 4 phonon effect. Interestingly, we find that the candidates towards the right side, where the 4 phonon effect is weak, include DCN compounds. What I mean by that is these compounds are composed of boron, carbon, and nitrogen on some other atom. And with this insight, we actually found out that by isotopically enriching boron nitride, the thermal conductivity could be significantly enhanced. So our calculations showed that the thermal conductivity of boron nitride, if isotopically enriched, can go up by a factor of 2.5. And we communicated this with our experimental colleagues, who were once again able to prove that our predictions are right. So all these different curves are different calculations involving both 3 and 4 phonon scattering for different isotopic compositions. For example, the green one is natural boron nitride and the red one is C10 boron nitride. And you can see that the experiments are lying on top of the theory. More importantly, the achieved thermal conductivity in the experiment is roughly 1800 watt per meter Kelvin at room temperature. To give you some context, diamond's thermal conductivity is around 2000 for the naturally occurring diamond. So this is quite comparable to that of diamond. So I'll just take a couple of minutes to show how we are able to even capture the failures of the conventional theory for thermodynamics as well. So in weakly bonded materials like sodium chloride, which is an ionic crystal, when you do the conventional quasi-harmonic approximation for the free energy, you see that the lattice constants are significantly over-predicted compared to the experiment. In the thermal conductivity also, if you do the full calculation, including 3 and 4 phonon scattering, the conductivities are much lower than the experimental measurements. And we found out, interestingly, that this failure of this conventional theory on thermodynamics is more fundamental in the sense that the phonon quasi-particle picture is itself breaking down. So for a phonon quasi-particle picture to work, gamma or omega should be much smaller than 1, gamma being the scattering rate and omega being the frequency. You can see that around 500 Kelvin, this assumption is broken down. So we developed a self-consistent renormalization theory, framework to fix this issue. This renormalization scheme was based on this loop diagram that I think you're all familiar with. And when we included this renormalization, we not only got excellent agreement with the experiments for lattice constants, the phonon quasi-particle picture is now well behaved. Gamma or omega is much lower than 1 for most phonons. And the thermal conductivity that we get, that is the red solid curve on the figure on your right, lies very close to the experimental data. So to summarize, I hope I have shown you the very predictive feature of this unified first principles framework, which includes both the lowest order conventional approach and higher order effects on phonon scattering and thermodynamics. And using this framework, I have worked on several problems involving materials discovery for energy transport. I also, as I introduced in the first slide, I also do some experiments, but for the interest of time, I won't be able to go into this. So yeah, thanks for your attention. I'd be happy to take any questions.
Yeah, thanks for a very nice talk. I think Shobna has raised her hand for a question. So Shobna, can you unmute yourself? And
yeah, thanks. That's very interesting work and great talk. I was just wondering, so you showed that 4 phonon processes are very important. Do you have any idea about why they contribute so much? Is it mostly because of the sort of joint density of states effect, or is it because of the matrix elements, or is it because of both?
It's a very good question. Let me see if I have a backup slide for that. Yeah, so by joint density of states, I'm assuming you mean this phase space, right? The number of
Exactly. Right? Yeah.
Right? So in whichever material we find 4 phonon scattering to be important, there's always a weak 3 phonon scattering phase space. So the lowest order scattering.
Sorry, can you repeat the last sentence again?
So in any material where we find a strong effect of 4 phonon scattering in strongly bonded materials like 3,5 compounds, we always find a weak 3 phonon phase space.
Okay.
So there is the lowest order scattering is weak because of some features in the dispersion and joint density of states. Okay. And 4 phonon scattering, just because of sheer combinatorics, does not get affected by the features of the dispersion.
Yeah.
So whenever you have, for example, a large mass ratio, you have a large AO gap that basically removes one channel, AAO, that is 2 acoustic and 1 optic channel, and that exposes other features in the dispersion. So eventually you get very weak 3 phonon scattering rates, and then 4 phonon scattering becomes comparable.
So it's mostly a phase space effect then? In
strongly bonded materials. In the case of sodium chloride that I showed at the end, it's a combination of both. Okay. It's both strongly anharmonic, and there is some phase space effect.
Okay, thank you.
Yeah.
I think Arindam has a question. So Arindam, please unmute yourself.
All right, thanks, Priya. Navaneeth, this is a really interesting talk. This is Arindam from IISc Bangalore.
Hi.
Hi. So I have a very short question. So this is regarding this phonon scattering, or even in conventional picture. These are all in the diffusive regime, if I understand correctly. And so what is your take on the importance of 4 phonon scattering as you start going down in the size of the sample? Suppose something goes down to in the order less than or close to the typical, the phonon mean free path.
Yeah, thanks. That was a good question. So yeah, right. If you take a very thin material sample, for example, you will have boundary scattering. So this 4-phonon scattering is actually can be treated on the same quote-unquote footing as 3-phonon scattering, in the sense that you can calculate an effective mean-free path combining both 3-phonon and 4-phonon scattering rates. And if that mean-free path is comparable to your system dimension, then the diffusive scattering becomes, at the boundary becomes important. So it's really a comparison between the length scale of your sample, temperature as another variable, and the material that you're using.
Okay, so you mean to say there is, I mean, the boundary determines the scale, and essentially the phonons, 4-phonon scattering is no longer.
That really depends on the material and temperature, right? If you go to low temperatures and if you take like diamond, the mean free path is several millimeters long.
Mm-hmm.
So, but if you take sodium chloride at 600 Kelvin, the mean free path is a few nanometers.
Right.
Okay. So, yeah, right. So if your device is comparable to that mean free path, it will be affected by diffuse scattering at the boundary.
Good. Thank you.
Yeah.
Yeah, I had a naive question. Since there are no other questions, let me ask it. Essentially, from your, at least from your results on boron nitride, I think you can't, without a calculation and without getting your phonon spectrum, you won't be able to say whether your 3-phonon or 4-phonon processes would be important. I mean, there are no naive rules which you can take.
Yeah, so that was the motivation for this work. We wanted to get some insight just by looking at the phonon dispersions, whether we can predict a material will have high strong 4-phonon effect or not. So this paper contains these selection rules that is related to the joint density of states, and you can identify based on just the dispersion which of these scattering channels will have anomalously weak joint density of states. What we find is in the case of 4-phonon scattering, the joint density of states is not sensitive to the features, specific features in the phonon dispersion. And additionally, we find that materials containing boron, carbon, and nitrogen atoms typically have weak anharmonicity. So with these 3 ground rules, we will be able to kind of predict this plot, for example. So if you look at the left-hand side, aluminum antimonide is a very large mass ratio compound, does not contain boron, nitrogen, or carbon. So you would expect with these rules that the effect of 4-phonon scattering will be strong. So it will give you a good picture, but of course, if you want to get very quantitative results, you have to do the full calculation.
Sure. Okay. Okay. Thank you very much.
Thank you.
So, yeah. So we now move to the next talk, which is, I think, a contributed talk. Is